Chapter 4, Axial Load, Stress and Axial Deflection Calculation in Members. Let's, let's solve a problem in a stress calculation for the equation provided. So this example we have a two uh, solid cylindrical shafts attached to each other and handling two forces. We want to determine axial stress in each part of this configuration. Let's approach the problem. So if we call this area A1, the diameter 1 of 20 millimeters, and this one area 2, that's a diameter to 15 millimeters. So if you want to calculate stress in each of these sections, stress is simply force over the area. So first of all, we need to calculate their areas. First of all, so A1 is pi over 4 d1 squared, and that's pi over 20 millimeters squared, and that's 314.2 10 to negative 6 meters squared. If you do likewise for A2, gives you 176.7 10 to negative 6 meters squared. That's A1 and A2 for the cross-sectional area which the force applied on it. So for the first part, for area 1, if we get the configuration from left to right, as we enter the second shaft from the left, we experience a of 10 kn. As we travel far to shaft 1, there is nothing, all just a 10 k kilonewton force. All of a sudden, just translate all this distributed force, because it just gives in a given a force of 30 kilonewton. So we can replace all of them with a concentrate of 30 kilonewton. Okay, so there is a pull of 10, there is a push of 30. So as we enter the first part, there is a push of kilonewton. Subtraction of these two forces, the 10 30 push just gives us a 20 push in second in area, which we call that area 1. So area 1, we already calculate the area. F1 is 20 kilonewton push. So we divide the force F1 20 kilonewton, our area just gives us 10 cube newton over the area for cylinder 1, which is 340.10 to negative 6. It just gives us a sigma 1 is equal to 63.65 megapascal, and pascal is newton over meter squared. And so sigma 1 is a compression, and also that's a 63.65 megapascal. For area 2, it's simpler because it just have a 210K at its box ends. The A2 is 176.7 F2 over all this F2. These are tensile force of F2. Just gives us a sigma stress. The second part is 56.59 megapascal. So sigma 2 is a tensile force, and the value of 56.50 megapascal. At the same time, if from chapter 4, sigma is stress is normal force over the area, epsilon is d delta, strain is d delta over dx. Small deformation over small change in distance, and based on Hooke's law, which is sigma is modulus of elasticity times the strain, and if you call this 1, 2, 3, and combine all of them together, it just gives us n over area, force over area is equal to modulus of elasticity d over dx. So if we rearrange this equation based off d delta, it just gives us n dx over ei is d delta. So d delta is n x dx over a times e. So again, delta has two scenarios for discrete separated parts, members, or continuous shape. So if that's the case for first case, for example, if you have a three solid shaft of A2, A3, A2, A1, A2, A3, and their delta, and you apply a force at, for example, 1N delta or formation, elongation at the example far end, delta B, for example, let's say, that's NILI summation of N1, L1, 1, A1 plus N2, 2, etc. If you have a continuous shape condition, so that's integration over 0 entire length of nx or over ex times ax dx, and that's for something like continuous low cross-sectional area. In our example, we want to determine the axial displacement on each portion of the rod if both are made from A36 steel. By A36 steel, we can easily verify that the modulus elasticity for that is SI unit is 200 gigapascal, and that's 210 to 9 Newton over meter squared. And if the length of each part is provided, so for example, part 1, delta 1 is N1 L1 over EA, both are steel, so there is no E1 and E2, both of them are the same. So 100 kilonewton converted to Newton times 1 meter over which is 210 to 9 Newton square, which is Pascal, times the area, cross-sectional area of 1, which is calculated that is equal to 314.36 meters squared. If you do the math, it just gives us delta 1 is equal in terms of millimeters. Likewise, do the same process for other area 2 is also axial force N2, which is this time 10 kilonewton times the length, which is 1.5 modulus elasticity remains the same, and area is 176.7 10 to negative 6 meters squared, and if you do the mass, it gives you delta 2. The function of second part is 0.075 millimeters. Solve more example next video.